السلام عليكم. Test. Okay, my name is Mr. Ahmed Ahmad, and in this presentation, I will be going through the 10 Advanced Physics Term 2 Heykel revision sheet. This will be a two-part series. In this first part, I'll be going through the multiple choice questions, so from question number 1 to 15. And hopefully in the second part, I'll be going through the open-ended questions. As a disclaimer, you should know that this is not a thorough revision. Rather, I'll be just going through the questions and highlighting any points I feel are worth mentioning. Second, I'd like to preface this by saying I'll not be using my graphic tablet. Unfortunately, I'm having technical issues with the pen, so I'll just be using the mouse. Okay, let's start with question number 1. Question number 1 states, state Ohm's law and apply to simple circuits, Ohm's law being delta V equals current times resistance, and define a resistor as a device designed to have a specific resistance and identify its SI units as ohms. So a resistor is a device which has a natural tendency to impede flow of charge. So it works, or it basically limits the amount of current flowing through it. And Ohm's law, stated over here, where R, resistance, equals the potential difference in volts divided by current. There are 3 variants of Ohm's law, you should know. This is the general form. And then when you have a circuit made up of multiple resistance, or rather resistances, then we can modify Ohm's law to this form, where Req is the equivalent resistance, delta Vs is the potential difference of the source. Most likely in the circuit you will come across it would be a battery, maybe a cell, and Is is the current through this source. So that's Ohm's law. And lastly, the third variant of Ohm's law is this variant, Rn equals delta Vn over In. This N, it corresponds to the resistor number in the circuit. So for instance, if you want to find the potential difference across resistor 3, then you would plug in R3 equals delta V3 over I3. Next, question number 2. Analyze simple electrical circuits that contain combinations of resistors and batteries and evaluate the current passing through each resistor and potential difference across them. So I suggest we solve this problem here. Example number 1. We have a potential difference source, this battery, and we have 2 resistors, R1 and R2. Given is the potential difference of the battery and the resistance of both resistors respectively over here. We can find multiple things relevant to this circuit. Number 1, we can find the equivalent resistance. Of course, you'll be able to identify this as a series circuit. Thus, the equivalent resistance is the mathematical sum of the resistances, the individual resistances. Substituting, we get the equivalent resistance. Then we can apply, because there are numerous resistors in the circuit, we can apply the modified Ohm's law. We know the potential difference of the source, thus we can find the current through the source Is. It just so happens that since this is a series circuit, the current through delta Vs, or the current through the battery, will be the same current through R1 and R2 as stated over here. Is equals I1 in this case equals 0.1. 3, read along, you can see how we can find delta V1, the potential difference across resistor 1, since we know that the current going through R1 is the same as the current going through the battery. Now we have two knowns. We know the resistance R1 and we know the current I1. We can find delta V1 using this variant of Ohm's law. Applying, you can feel free to pause, of course, and follow along. We can do the same, of course, with delta V2. Moving on, of course, this was just an example. In this case, it was a series circuit. It could be a parallel circuit. In the case of a parallel circuit, you'll have to keep in mind the difference between series and parallel circuits. So for a series circuit, these are the relationships between the potential differences across individual resistances and the battery, as well as how to find the equivalent resistance, as well as the relationship between the currents. And now for a parallel connection, the potential differences are the same across all branches. The current splits at a junction and then reunites at the junction nearest to the negative terminal of the battery. And of course, I'm sure you've come across this formula on how to find the equivalent resistance of a parallel circuit. This is a second example. Question number 3. State Ohm's law and identify devices which obey Ohm's law and apply it to simple circuits. Delta V equals IR. Ohm's law, one thing I would like to highlight, Ohm's law, R equals delta V over I. This relationship this relationship, R equals delta V over I, this is a linear relationship. When you look at the relationship between delta V and I, if we rearrange, then we get delta V equals IR. So the potential difference is directly proportional to the current. In other words, if we increase the potential difference across a resistor, then the current should increase linearly. Resistors come in different different forms. Some may not have a linear relationship. If they do not have a linear relationship, then we cannot say they obey Ohm's law. We cannot say they obey Ohm's law. Now, one thing I will just say out loud, and I wish you have a pen and paper so you can follow along. Imagine we had a circuit, just a regular circuit consisting of a battery, one resistor, and an ammeter in series with this resistor. Now, I want you to draw a graph. On the x-axis, we have the potential difference. So an independent variable, a variable we can control. And on the y-axis, current. On the y-axis, current. Now, if we, as measured in the ammeter, now if we increase the potential difference of the battery, then the resulting current would follow a linear relationship with the potential difference. A linear relationship with the potential difference. Now, if you were to measure the slope being the rise over the run, so I over delta V, this doesn't have any physical relevance. However, this quantity, if you were to take the inverse of this quantity, so the reciprocal, so you flip it, you would actually find the resistance of the resistor. So R equals delta V over I, which equals 1 over the slope. So R equals 1 over the slope. Moving on, question number 4. Explore connecting resistors in series and parallel and determine the properties of and uses of each kind of connection by studying the electric current and potential difference across each resistor. So, as stated before, in a series circuit, the potential difference of the energy source equals the potential difference across each energy consuming device. We're talking specifically about series circuits. As for the current, it would be the same throughout the entire circuit because there's only one path for the current to flow. And as for the resistance, the equivalent resistance equals the mathematical sum of each individual resistor or resistance. As for parallel circuits, the potential difference across each branch is the same. The current splits at each junction and reunites at the junction closest to the negative terminal of the battery, and the resistance, equivalent resistance, follows this relationship. So, for instance, over here, if we were to measure the potential difference across R1, since this is a parallel circuit, then delta Vs equals delta V1. So the delta V of R1 would be 12 volts. Follow along. You can see how you can apply Ohm's law to find the current across or through resistor 1, the current through resistor 2. And also you can find the current through the source by applying Req equals delta Vs over Is. Moving on. Explain how current in transmission lines are altered to reduce thermal energy transformations. So just a moment there. Now, in a high voltage transmission line, as we call them, the transmission lines, looking for a figure here. In the high voltage transmission lines, we have electrical losses. These manifest as heat. Now, the power loss through these transmission lines equals P equals I squared R, where I is the current through the transmission line and R is the resistance. Of course, this value is undesirable. This value is undesirable. So we want to minimize this as much as possible. In fact, it would be more beneficial to reduce the current than it is to reduce the resistance because of this squared here, which means that if we have the current due to the square, the presence of the square sign, then we will quarter the power loss. Now, how can we reduce the current flowing through the wire? It would be by increasing the voltage. So how do we decrease the current and thus decrease the power loss? It would be by increasing the voltage. That's why these transmission lines oftentimes have quite substantial potential difference across them, it could range to hundreds of thousands of volts. Reason being is to reduce the current as much as possible. By reducing the current, we can minimize the power loss through the line. Moving on. State Kirchhoff's loop junction rule and relate them conservation of energy, charge, and apply Kirchhoff's loop and junction rule to electric circuits. So now we will be going through the Kirchhoff rules. The Kirchhoff rules have other names. The Kirchhoff voltage law or rule is known as the loop rule, and the Kirchhoff current law or rule is known as the junction rule. Now, as for the KVL, as we oftentimes call it in class, it's based on the principle of conservation of energy. So the energy entering a loop is equal to the energy being consumed by the loop. And another way of saying it is saying that the potential difference in equals the potential difference out, since potential difference or voltage equals the amount of energy per unit charge. So voltage is related to energy here, we could see. And as for KCL, Kirchhoff current law, it is based on the conservation of charge. So the current entering into a junction equals the current leaving that junction. So let's take, for example, let's take this example number 3 here. I highlighted in red a loop. So we have a battery, 2 resistors in series to each other. So R1 and R2 are in series to each other. And then we have a third resistor, R3, parallel to them. Given is the potential difference of the battery and the potential difference across resistor 1. We would like to find potential difference 2. Now, this is a combined circuit. This is not a series, nor is it a parallel circuit. It is a combined circuit. So one way we can find delta V2 here quite quickly is by applying the loop rule. The loop rule statement is the potential difference in equals potential difference out. Of course, the battery here is supplying energy, so we will consider this 15 volts as delta V in, while this 9 volts of the potential of the resistor 1, it's consuming energy, so we will consider it delta V out. So by applying the loop rule, delta Vs equals delta V1 plus delta V2, we can substitute and find delta V2. As for the junction rule, let's consider this figure here. For the example, we have I1 being here, equals 2 amps. It's entering, so pay attention to the direction of the arrow. So the arrow is pointing towards this junction A. So this I1 will be considered I in. We have I3 leaving the junction. Pay attention to the direction of the arrow there. It's leaving the junction. And the question is asking for the value of I2. So we'll apply KCL, current in equals current out. So I1 equals I2 plus I3. Substituting, we can find I2. 7. Analyze simple electrical circuits that contain combinations of resistors and batteries and evaluate the current passing each resistor and potential difference across it. So this is just a repeat of the previous questions. I will not go through that again. Question number 8. Explain the importance of voltage divider circuit to achieve a desired potential difference. 2. Identify a type of variable value resistor whose value depends on the presence of certain factors such as heat, light, etc. Okay, let's go through variable resistors and the voltage divider circuit. So this is a voltage divider circuit. They are essentially series circuits, and they're used to draw a potential difference less than that of the source. So for instance, you have a battery with a potential difference of, let's say, 12 volts. But I have an electrical element which I would like to restrict the potential difference going across it. So I may resort to using a voltage divider circuit. How is this done? This is done by having a series circuit made of two resistors and then combining, or rather attaching or installing my device parallel to one of the resistors. So let's think about it here. So we have the battery and we have R1. This is a variable resistor in this case, and R2. And here, let's explore what happens to the potential difference across R2 when we adjust the resistance of the potentiometer R1. Now, the relationship between the potential difference across R2, meaning delta V2, and the value of the two resistances and the potential differences of the battery is given by this formula here, which is delta Vn n. So you select one of the resistors you would like to calculate the corresponding voltage for. So for instance, if we were exploring or trying to calculate the potential difference across R2, we would plug in delta V2 equals delta Vs times Rn, being R, in this case 2 over R equivalent. So let's solve this example. We have a series circuit. This is the example we solved, but in this case, we will be applying the voltage divider circuit equation. Here, they calculated delta V1 rather, or I calculated delta V1 rather than delta V2. Now, let's go back and discuss what's actually happening here. Let's go back to this figure here. So if we want the potential difference across R2 to increase, then we want the ratio of the resistor 2 to resistor 1 to increase. How we can do this is by decreasing R1. I like to think of this in terms of energy. So the greater the resistor or the resistance, the more energy will be allocated to that resistor or will be consumed by that resistor. So let's say we have R1 and R2. If R1 is greater than R2, then the potential difference across R1 will be greater than the potential difference across R2, and vice versa. So if I want more energy to end up on R2, then I want the resistance across R2 to be greater than the resistance of R1. So what I can do is adjust this potentiometer, decrease its resistance, and by decreasing its resistance, then the ratio of R2 to R1 increases. Thus, I will end up with more energy being allocated to R2 or consumed by R2. Please go through this example. Feel free to pause and try to find delta V1 and delta V2 using this formula. Question number 9. Relate the electric power of or rate of energy transfer to current and potential difference P equals I delta V. Identify the appropriate current rating of a fuse in a circuit. So in this question, sorry, so in this question, we'll apply P equals I delta V. Power is in watts, I is in amps and delta V is in volts. To identify the appropriate current rating of a fuse in a circuit. So typically, let's actually build a circuit very quickly. So here we have a simple circuit. And we will be using this fuse as a safety device. So this fuse has a rating. So currently the fuse rating is 4 amps. And let's measure the current going through the circuit when it's closed. So currently it's at 0.9 amps. Now let's hypothetically say, that this resistor will, or let's say another component, for example. This bulb, for instance. This bulb will explode. Let's say this bulb will explode if the current exceeds 2 amps. So this can happen due to numerous reasons. One of them being we have a short circuit, but we can model this explosion by just increasing the potential difference across the battery. So we said the current exceeding 2 amps will cause the battery to explode. So by increasing the potential difference of the battery, there we go. Now we have an exploded bulb. So one way to protect our bulb or our electrical device here is by using a fuse. Now the fuse must always have a rating less than the threshold current, or the current which may cause problems. So we would use a rating of, let's say, suppose 1.7 amps. 1.7 amps. Now, let's follow along now what happens. So our battery, I'm sorry, our light bulb is experiencing a current of 1 amps. This should not damage it. However, if the current starts to rise, as it is now, if it reaches 2 amps, then our bulb will explode. However, the fuse has been set to 1.7 amps. So the moment the current exceeds 1.7 amps, the fuse will melt and open the circuit, thus protecting our electrical device. So the fuse rating must be at the very most equal to the current which might cause damage. There's an example I would highly suggest you. It's in the book. Mm, let me just recall, where is this example? Yeah, this example here. This example, it relates power to current to voltage. This example here, Unfortunately, my version of the book has different numberings to the one you might have at home. So just feel free to pause and go through this page. This page relates power to potential difference, to current, and to fuse ratings. This example should suffice when it comes to the aforementioned question. Moving on, describe properties of magnets. Describe the forces that occur when like or unlike poles of two magnets are brought close together in terms of interaction. Okay, so now we will be discussing magnets. Just bear with me here. So magnets, as we know, they have two poles. We call magnets polarized because they have two poles. There are no magnetic monopoles, meaning they must always exist with two poles, regardless of how they look, of their shape. And of course, the general rule is that like poles repel and unlike poles attract. Other properties of magnets, if you break down magnets to smaller pieces, they will still have two poles or brought closer in terms of interaction between magnetic fields and orientation of the magnetic field lines. As for the direction of magnetic field lines and their general shape, let's have a look. So these are magnetic field lines. Of course, we cannot see them with our naked eyes, but we can use iron filings sprinkled on top of a white sheet to observe the magnetic field lines. Here's a 3D view. And outside the magnetic field lines point from north to south, inside the magnet from south to north. And always you should remember that a compass will point in the same direction as the field lines. Okay, for question number 12, I'm sorry, 11, describe how magnetic materials can be turned into temporary magnets. Describe magnetic domains and relate them to magnetic properties of ferromagnetic materials. So let's consider this nail. This nail is originally non-magnetic. However, when it comes into contact with a permanent magnet, then it now adopts the properties of the magnets and it becomes what we call magnetized. So this is called a temporary magnet. The moment we remove the nail from the magnet, it will no longer exhibit these traits. So this is a temporary magnet. So this is one way of causing a material to become temporarily magnetized. Another way is to run a current through a material. So as we can see here, we have this wire currently with the current off. The moment we turn the current on, meaning current passes through the wire, a compass will become disturbed. This suggests the presence of a magnetic field around this wire. The magnetic field around a straight wire appears to be concentric circles, and the direction of the magnetic field follows the right-hand rule. So the thumb is in the direction of the current and the fingers wrap in the direction of the magnetic field. Common symbology you might come across is an X. An X represents current going into the page and the dot represents current going out of the page. Now, why does a material become magnetized or um, exhibit magnetic behavior is due to domains. Now, these domains, let me find you the. These domains are a group of similarly oriented atoms. So atoms, they also have two poles. This is an easier way to understand magnetism, is that atoms have two poles, north and south. Now, if a group of atoms are all pointing in the same direction, we call this group of atoms a domain, represented by an arrow. Now, if a material is non-magnetized, then these domains are randomly oriented. However, if a material is magnetized, then it will follow a more regular orientation or pattern. Moving on. Let's go to the coil and see what a magnetic field looks like around a coil. Electromagnetism, we saw the current around a straight wire. Now for the current going, now for the magnetic field around a coil. Now a coil with a current passing through it will induce a magnetic field around it, which looks very similar to the magnetic field around a bar magnet. Now, in determining the direction of the magnetic field, we use a modified right-hand rule. In this case, the fingers wrap around the coil in the direction of the current, and the thumb points in the direction of the magnetic field. So, for instance, here, current is going from positive through the coil to negative terminal. So it goes up and wraps from around and behind the coil or the this core, and then it wraps to the bottom and comes out of the page, then back up into the page, down out of the page, back up, and so on. So wrap your hands around as such, and your thumb should point in the direction of the magnetic field, leaving from north, going around and entering south. Question number solenoid. Okay, let's add a few more points about solenoids. Now, this magnetic field, we can adjust its strength by doing the following. We can increase the strength of the magnetic field around the solenoid by increasing the current, by increasing the number of loops, or by using a ferromagnetic core. So, for instance, by sticking a nail or a piece of iron through the coil. Fourthly, by decreasing the distance between the individual loops. Moving on to question number 13. Define magnetic flux and its relation to the number of magnetic field lines that cut perpendicularly through a unit area. So flux refers to the number of lines. Now, the number of lines, you should know, is indicative to the strength of the field. So the more the number of lines per unit area, then we have a stronger magnetic flux, what we call density, and this is proportional to the strength of the field. I would like to sketch this actually. I think it's important. Let's say we have these two magnets. Now, one way to determine which magnet is stronger is by counting the number of lines. But what some students they confuse is how to count the lines. So what I would suggest is split the magnet into two, such. And now count the number of lines. What reason I do this is so that you don't count the same line twice. So that's 1, 2, 3, 4. That's 4 lines. As for the magnet on the left, on the right would be 1, 2, 3, 4, 5, 6, 7, 8. So 8 to 4. So this you could argue, I don't necessarily believe it's true, but you could argue, because I've seen a past paper question asking how many times stronger is the magnet on the right compared to the magnet on the left. Well, the ratio of field lines is 4 to 8, which is 1 to 2. So you could say that this magnet on the right is twice as strong as the magnet on the left. Question number 14. Apply the right-hand rule to determine the direction of the force acting on a charged particle move in a magnetic field. So let's go ahead and do that. So if we have a single charge moving through a magnetic field. So let's consider this example in the figure here, in the figure. This middle one. Ignore this one, ignore that one. Let's just focus on this one. We have a positively charged particle moving through a magnetic field. Here we have two magnets with the relevant orientations given. So the magnetic field points from left to right, from north to south. Now, how do I determine the direction of the force acting on this charge? I use the right-hand rule. The right-hand rule says that I point my thumb, of course, my right hand, my thumb in the direction of the motion of a positive charge, my fingers in the direction of the field, so from left to right, and my thumb being out of the page. If we do this, my thumb out of the page, my fingers to the right, then the force is with the palm. It should say here the palm, كف اليد, يعني كف اليد. So the direction of the force should be upwards. Now, what do we do if the charge is negative? If the charge is negative, then we will reverse the direction of the thumb. So for instance, in this example here, this is a negative charge moving out of the page. So instead of my thumb pointing out of the page, I'll point my thumb into the page. So my thumb pointing into the page, my fingers pointing from left to right with the direction of the magnetic field. My palm will point downwards with the same direction as the force. Finally, explain how a current carrying conductor placed in an external magnetic field experiences a magnetic force. Now, the reason this current carrying conductor placed in an external magnetic field experiences a magnetic force is actually, let's see this in a simulation. So I'll open this simulation. Your teacher might have shown you this. So here we have a current carrying wire. And if we take a 2D view, we can see the magnetic field around this wire. Now, if we place the same wire through a magnetic field, then it will experience a force. Now, why is this? Now, there are a lot of explanations as to why this happens. I find an easy one is the interaction between the magnetic field between the permanent magnet and the magnetic field of the current carrying wire. This interaction causes a force, causes there to be a force. I will not get into the deep explanations offered on the internet and in the book. What I will just highlight and discuss is how do I determine the direction of this force. So let's do that now. Of course, this is the working principle behind how a motor turns. Let's find this is the right-hand rule. So We have a current carrying wire placed inside a magnetic field. My thumb will point in the direction of the current. My fingers point in the direction of the field, and the force will be in the direction of my palm. Of course, don't confuse. I've seen many students do this error, is that they use their left hand. Make sure to use your right hand. And that concludes this part one of this series. I hope you have benefited from this. I wish you all the best. بالتوفيق جميعا وكل عام وأنتم بخير.